There is something wonderfully strange about a black hole. Light is the fastest thing in the universe. It has no rest mass, it never slows down in a vacuum, and yet once it crosses a black hole's event horizon, even light cannot find a way back out. So what exactly is holding it there? Welcome to the Snoozy Scientist. I'm very glad you've joined me tonight. Before we settle into things, let me know where you're listening from. Maybe you're tucked into bed with the lights already low, stretched out on the sofa after a long day, or listening through headphones while the rest of the world grows a little quieter. Wherever tonight has found you, get comfortable, let your thoughts wander, and we'll take this one slowly. And if these gentle science journeys are becoming part of your evenings, a like and a subscription are always greatly appreciated. They help this little corner of science continue to grow. And if you're already subscribed, thank you for coming back and spending another quiet evening here. Tonight we're heading toward one of the strangest boundaries anywhere in the universe. Hopefully not too quickly. Black holes do have a reputation for being rather difficult to leave, because the surprising answer is that a black hole does not trap light by overpowering its mass. Light has no rest mass to overpower in the first place. The real explanation is much stranger, and it changes the way we have to think about gravity itself. So, get comfortable, and let's begin. How can a black hole trap light? If light has no mass? At first glance, there seems to be something wrong with the idea of a black hole trapping light. Gravity, after all, is often introduced as a force that pulls on things with mass. The Earth pulls on the Moon, the Sun holds the planets in orbit. Drop a stone, and the Earth pulls it toward the ground. So if light has no mass, then why should gravity have any effect on it at all? It is a perfectly reasonable question. In fact, the confusion comes less from anything strange about light, and more from the way gravity is usually introduced. To begin with, when physicists say that light has no mass, they mean something very specific. A photon, the quantum particle associated with light, has zero rest mass. That does not mean it has zero energy. It does not mean it has zero momentum. And it certainly does not mean that it is somehow disconnected from gravity. A photon can carry energy across billions of light years of space. It can strike an atom and transfer that energy. It can push very gently on a reflective surface through radiation pressure. It can even contribute, in principle, to the gravitational influence of a system, because energy itself is part of what gravity responds to in Albert Einstein's general theory of relativity. So massless does not mean insignificant. The photon is the quantum of the electromagnetic field. In modern physics, light is not described simply as a stream of tiny glowing pellets flying through empty space. It is an excitation of the electromagnetic field, and under the right conditions that excitation behaves in ways we recognize as individual photons. Albert Einstein played an important role in this story in 1905 when he argued that light energy was exchanged in discrete packets. That idea helped explain the photoelectric effect, in which light can eject electrons from certain materials. Much later, the quantum description of light became part of quantum electrodynamics, the theory describing how light and electrically charged particles interact. None of that gives the photon rest mass. And yet photons are clearly affected by gravity. Light passing close to the Sun bends slightly. Light travelling past galaxies can be redirected much more dramatically. Entire clusters of galaxies can act like enormous gravitational lenses, warping the appearance of even more distant objects behind them. Around black holes, the bending becomes so extreme that some light can circle the black hole before either escaping or falling inward. The reason this can happen is that the familiar picture of gravity as a force pulling directly on mass is not the complete description. Isaac Newton's theory of gravity works extraordinarily well in many everyday situations. It can describe falling objects, planetary orbits, tides, and much of the motion we see in the solar system. But black holes push gravity into a regime where the deeper description developed by Albert Einstein becomes essential. In general relativity, gravity is not simply an invisible rope stretching between massive objects. Mass and energy alter the geometry of spacetime, and once spacetime is curved, everything travelling through it must follow the paths allowed by that geometry. That includes planets, it includes falling astronauts, and it includes light. This is the first major shift in thinking that makes black holes easier to understand. A photon does not have to possess rest mass for its path to be influenced by gravity. The geometry through which it travels is already curved. Imagine drawing a perfectly straight line on a flat sheet of paper. Now imagine trying to draw the equivalent of a straight path across the surface of a sphere. Locally, the path can still be as straight as possible, but when viewed across the curved surface, it behaves very differently from a straight line on a flat page. Space-time around a massive object works in a much more sophisticated way, but the broad idea is useful. Light follows the natural paths available through curved space-time. A black hole simply takes this curvature to an extraordinary extreme. One of the most important details is that gravity does not slow a nearby photon until it somehow becomes stuck. Locally, light in a vacuum always moves at the speed of light. A photon passing near a black hole still moves at the speed of light when measured by a nearby freely falling observer. A photon crossing an event horizon also moves locally at the speed of light. It does not hit the horizon like an insect meeting a window. It does not suddenly become heavy. It does not gradually grind to a halt. The event horizon is not a solid surface at all. It is a boundary in space-time. And that changes the question completely. Instead of asking whether the black hole pulls hard enough on a massless photon, it is better to ask what possible future paths remain available to that photon. Far away from a black hole, a beam of light aimed outward can keep travelling outward. The surrounding space-time allows a future path that leads farther and farther away. Close to a black hole, those possible paths become increasingly distorted. And once the photon is inside the event horizon, every future directed path available to light leads deeper into the black hole. This does not happen because the photon is too slow. Nothing outruns light locally. It happens because there is no longer an outward route through space-time that leads back to the external universe. In that sense, a black hole does something much stranger than simply overpowering light. It changes what the word outward can mean. The deepest part of the puzzle is therefore not really about the mass of the photon at all. It is about causality. It is about which events can still influence which other events, and it is about how gravity can reshape space-time so profoundly that even something travelling at the universal speed limit can discover that every possible future lies in the same direction. Saying that a photon has no mass sounds simple, but the statement carries more meaning than it first appears to. In everyday life, mass is usually associated with heaviness. A stone has mass. A car has mass. The Earth has a great deal of mass. It is natural to imagine that if something has no mass, then it must somehow have no physical substance, no momentum, and perhaps very little ability to interact with anything else. Light immediately shows why that intuition is incomplete. A photon has no rest mass. The word rest is important, because rest mass refers to the mass an object has when measured in a frame where that object is stationary. For an ordinary particle such as an electron, this is straightforward. In principle, You can imagine moving alongside the electron until it appears at rest relative to you, and then describing its properties in that rest frame. A photon is different. There is no valid reference frame in which a photon is sitting still. In a vacuum, every local observer measures light moving at the same universal speed. You cannot chase after a photon and gradually reduce its speed relative to yourself until it finally stops beside you. No matter how quickly you move, light still passes you at the speed of light. This behavior is built into Albert Einstein's special theory of relativity. Special relativity connects space, time, energy, momentum, and mass in ways that are quite different from ordinary low-speed intuition. The famous relationship between mass and energy is often summarized by the statement that energy equals mass multiplied by the speed of light squared. But that familiar expression applies most directly to the rest energy of an object. The more complete relationship also includes momentum. Written in words, it can be expressed as energy squared equals momentum multiplied by the speed of light, all squared, plus rest mass multiplied by the speed of light squared, all squared. For a photon, the rest mass part is zero. That does not force the photon's energy to become zero. Instead, the relationship simplifies so that the photon's energy is directly connected to its momentum. A photon can therefore be completely massless in the rest mass sense, while still carrying both energy and momentum. This is not just a mathematical technicality. Light can push things. The effect is normally tiny, but it is measurable. When photons strike a surface and are absorbed or reflected, they transfer momentum to that surface. This produces radiation pressure. Sunlight, for example, exerts a very small pressure on anything it strikes. The force is far too weak to notice on your hand, but across a large enough reflective surface and over enough time, it can become useful. Solar sails are designed around exactly this idea. A spacecraft carrying a broad, lightweight reflective sail can receive a steady push from sunlight. No fuel has to be thrown out of the back of the spacecraft for that particular source of acceleration. The incoming photons transfer momentum directly to the sail. The same basic physics affects tiny particles of dust, atoms, gas, mirrors, and many other systems exposed to radiation. So even though photons have no rest mass, they are certainly not physically empty. The relationship between photon energy and light frequency emerged gradually during the development of quantum theory. Max Carl Ernst Ludwig Planck discovered that energy exchanged between matter and radiation could be described in discrete amounts. The energy associated with a quantum of radiation is proportional to its frequency. In words, the relationship is photon energy equals Planck's constant multiplied by frequency. Higher frequency light therefore carries more energy per photon than lower frequency light. Albert Einstein extended this idea in 1905 when he used light quanta to explain the photoelectric effect. Experiments showed that shining light on certain materials could cause electrons to be emitted. The surprising detail was that increasing the brightness of low-frequency light did not necessarily eject electrons, while sufficiently high-frequency light could. Albert Einstein explained this by treating the incoming light as arriving in discrete packets of energy. Each photon carried an amount determined by its frequency. If that energy exceeded the threshold required to free an electron from the material, the electron could be released. This provided strong evidence that the energy of light could behave in a particle-like, quantist way. And still, none of these photons needed rest mass. In fact, being massless is intimately connected with why photons travel at the universal speed limit. Objects with non-zero rest mass can move more and more quickly as energy is added to them. But pushing such an object all the way to the speed of light would require an unlimited amount of energy. Massless particles behave differently. In vacuum, they travel at the invariant speed of light. So the absence of rest mass is not a weakness that makes light somehow less physical. It is part of what gives light its distinctive behavior. A photon has no ordinary rest frame. It has no rest mass. Yet it carries energy. It carries momentum. It can transfer both to matter. It can alter atoms, heat surfaces, push mirrors, and travel across the observable universe. And those properties become especially important when gravity enters the picture. In general relativity, gravity does not respond only to rest mass. Energy matters. Momentum matters. Pressure and stresses matter as well. The source of gravitational curvature is the full energy and momentum content of matter and fields. That means the phrase "light has no mass" can never be translated into light, has nothing for gravity to work with. The photon is massless, but it is not exempt from the structure of spacetime. If anything, its masslessness makes its relationship with spacetime unusually clean. A photon simply follows the path available to light, and near a black hole, those available paths can become very strange indeed. For a long time, the most successful description of gravity came from Isaac Newton. In Newton's theory of universal gravitation, every object with mass attracts every other object with mass. The strength of that attraction depends on the amount of mass involved and on the distance between the objects. Double the distance, and the gravitational pull becomes 4 times weaker. Triple it, and it becomes 9 times weaker. For planets, moons, falling stones, and countless other situations, this works beautifully. But if gravity is described only as a force acting between masses, light creates an awkward question. A photon has no rest mass. So if one simply looks at the Newtonian gravitational force law and imagines putting zero mass into the place occupied by the photon, it appears that the force on the photon should also become zero. No force, no deflection, no reason for light to fall toward anything, and certainly no obvious reason for a black hole to prevent it from escaping. This is where the paradox begins to take shape. Strangely enough, the idea that gravity might trap light appeared long before black holes were properly understood. In 1783, the English natural philosopher John Michell considered an extraordinary possibility. He knew that the escape velocity from an object becomes larger if the object becomes more massive or more compact. Escape velocity is the speed an object needs, in the Newtonian picture, to move away from a gravitating body and never fall back, assuming it receives no further propulsion. For Earth, escape velocity from the surface is roughly 11 kilometers per second. For the Sun, it is roughly 618 kilometers per second. John Michell asked what would happen if a star were so massive and so compact that its escape velocity became greater than the known speed of light. At the time, light was often discussed in terms that allowed it to be imagined as corpuscles, tiny particles that might behave somewhat like ordinary matter. Michell reasoned that if these particles of light could not move quickly enough to escape the star's gravitational attraction, then the star would become invisible from far away. It would effectively be a dark star. Several years later, Pierre-Simon Laplace explored a similar possibility. These ideas can sound remarkably like predictions of black holes, and in a broad historical sense they certainly anticipated part of the mystery. But a dark star in Newtonian physics is not the same thing as a black hole in general relativity. The resemblance is useful, but it can also be misleading. The Newtonian escape velocity can be written in words as escape velocity equals the square root of twice the gravitational constant multiplied by the mass and divided by the radius. If the escape velocity is then set equal to the speed of light and the expression is rearranged, something rather interesting happens. The resulting radius has the form radius equals twice the gravitational constant multiplied by the mass and divided by the speed of light squared. That is the same mathematical expression that appears for the Schwarzschild radius of a non-rotating black hole in general relativity. This coincidence is striking. It can make the Newtonian explanation seem almost suspiciously successful, but matching one mathematical expression does not mean the physical stories are the same. In the Newtonian picture, light would be imagined as something trying to climb outward through a gravitational force, gradually losing the ability to escape in much the same way that a thrown stone might rise, slow, stop, and fall back. A genuine black hole does not work like that. Light near a black hole does not locally slow down below the speed of light. A photon crossing an event horizon does not run out of speed. And the event horizon is not simply a place where gravity becomes so strong that an outward moving object fails a contest between its velocity and an opposing force. The deeper problem is that Newtonian gravity treats space and time as a fixed background. Space is simply there. Time passes uniformly. Gravity acts across that stage as a force between objects. That framework has no true concept of spacetime geometry. It has no light cones determining causal structure. It has no event horizon in the modern relativistic sense. It cannot fully describe gravitational time dilation, because time itself is not dynamical within Newton's theory. And it cannot explain what happens when spacetime becomes so strongly curved that every future directed path inside a certain boundary leads inward. This is why trying to understand a black hole entirely through Newtonian gravity eventually creates confusion. Newton's theory remains extraordinarily useful whenever gravitational fields are weak and speeds are comfortably below the speed of light. It is not wrong in the situations where it works. It is incomplete. Black holes simply live in a part of nature where that incompleteness becomes impossible to ignore. Albert Einstein's general theory of relativity replaces the old picture with something much more profound. Instead of gravity being only a force acting through an unchanging background, gravity becomes connected to the structure of spacetime itself. Mass and energy influence spacetime geometry. That geometry then determines the paths available to matter and light. This is the conceptual step that the old dark star argument could not take. A photon does not need rest mass in order to follow curved spacetime. And once an event horizon forms, the central question is no longer whether gravity can pull hard enough on the photon. The question becomes whether spacetime still provides any possible outward path at all. That distinction is subtle, but it changes almost everything. The Newtonian picture asks whether light can fight its way free. General relativity asks something stranger, whether freedom still points outward in the first place. One of Albert Einstein's most important steps toward a new theory of gravity began with a remarkably simple thought. Imagine being inside a sealed laboratory with no windows. If the laboratory were standing on the surface of Earth, you would feel your feet pressed against the floor. Drop an object, and it would fall downward. But now imagine that the same laboratory were floating far from any planet or star, while a rocket engine accelerated it steadily upward. You would still feel yourself pressed against the floor. Drop an object, and the floor would rise to meet it. From inside the laboratory alone, those two situations could appear remarkably similar. This idea became central to what Albert Einstein called the equivalence principle. In its simplest form, the equivalence principle says that, over a sufficiently small region, the effects of a uniform gravitational field and the effects of acceleration can be locally indistinguishable. That sounds modest, but it has enormous consequences. Consider what happens if a beam of light enters one side of an accelerating laboratory. Imagine the laboratory accelerating upward, while the light travels horizontally across it. The light itself continues along its path, but during the brief time it takes to cross the room, the laboratory has moved slightly upward. To the observer standing inside, the beam therefore appears to curve downward relative to the walls. Nothing has grabbed the photon, nothing has slowed it. The laboratory has simply accelerated while the light was travelling across it. Now apply the equivalence principle. If acceleration can make the path of light appear curved, and acceleration is locally equivalent to gravity, then a gravitational field should also affect the path followed by light. That conclusion is crucial. The photon does not need rest mass in order for gravity to influence where it goes. Albert Einstein gradually developed this idea into a much deeper theory. In 1915, he completed the general theory of relativity. Gravity was no longer described simply as a force pulling objects through fixed space. Instead, space and time became part of a combined structure called spacetime, and the geometry of spacetime itself could change. Energy and momentum influence that geometry. Matter, radiation, and other forms of energy contribute to how spacetime curves. Objects then move through this curved geometry along the natural paths available to them. For a freely falling planet, that path can look like an orbit. For a falling stone, it can look like a descent toward Earth. For a photon, it can look like a bent ray of light. The photon does not need to possess rest mass, because the effect is not based on gravity selecting only objects that have mass and pulling them sideways. The geometry through which the photon travels has changed. An early and famous test of this idea involved the Sun. Albert Einstein predicted that light from a distant star passing close to the Sun should be deflected because of the Sun's gravitational field. Normally, stars appearing close to the Sun in the sky cannot be seen because sunlight overwhelms them. A total solar eclipse provides a brief opportunity to photograph the surrounding stars while the Sun itself is hidden. In 1919, expeditions associated with Arthur Stanley Eddington and Frank Watson Dyson observed the total solar eclipse from the island of Principe off the west coast of Africa and from Sobral in Brazil. The apparent positions of stars near the eclipsed Sun were compared with their positions when the Sun was elsewhere in the sky. The measurements indicated that the starlight had been displaced in a manner broadly consistent with Albert Einstein's prediction. The historical observations were far less precise than the measurements available today, and later analysis has examined the limitations of the original data carefully. Even so, the eclipse result became one of the events that brought general relativity to worldwide attention. Light, apparently, did not travel past the Sun as though gravity were irrelevant. Its path was bent. Modern astronomy now observes this effect constantly and with vastly greater precision. It is known as gravitational lensing. A galaxy can bend the light of another galaxy lying far behind it. A massive galaxy cluster can stretch distant galaxies into arcs. Under suitable alignment, a distant source can even appear as a luminous ring known as an Einstein ring. Compact objects produce still stronger distortions of nearby light paths. These are not rare philosophical curiosities. They are practical tools used by astronomers to map matter, study distant galaxies, detect otherwise difficult objects, and investigate the distribution of mass throughout the universe. And they reveal the central point very clearly. Light does not need rest mass in order to respond to gravity. The old question asks how gravity can pull on something massless. General relativity changes the question. The photon is already moving through spacetime. If spacetime is curved, then the natural path available to that photon can curve as well. Near the Sun, that produces a tiny deflection. Near a galaxy, it can produce spectacular lensing. And close to a black hole, the geometry can become so extreme that the range of possible paths for light changes completely. The remarkable thing is not that gravity somehow finds a hidden mass inside the photon. There is no hidden mass required. The remarkable thing is that gravity changes the stage itself. And once space-time is no longer flat, even light must follow the shape of what is there. One of the deepest changes introduced by relativity is the idea that space and time are not separate things quietly existing alongside one another. They are woven together. The mathematician Hermann Minkowski helped make this clear in the years after Albert Einstein introduced special relativity. He showed that the equations of relativity could be understood more naturally if 3 dimensions of space and 1 dimension of time were treated as parts of a single 4-dimensional structure. That structure became known as spacetime. This does not mean that time is simply another direction exactly like left, right, up or down. Time behaves differently within the geometry, but space and time are connected closely enough that changing how one observer moves through space also changes how that observer measures time. Once gravity enters the picture, the geometry becomes even more interesting. In general relativity, spacetime is not merely an empty stage upon which planets, stars and photons move. Spacetime itself can be curved, and this changes how motion should be understood. In everyday language, we tend to imagine an object moving in a straight line unless some force pushes or pulls it away from that path. Throw a ball and gravity pulls it downward. A satellite circles Earth because gravity is constantly dragging it away from the straight path it would otherwise follow. That description works well enough in Newtonian physics. General relativity offers a different perspective. A freely falling object is not necessarily being forced away from its natural path. It is following its natural path through curved spacetime. That path is called a geodesic. A geodesic can be thought of as the closest relativistic equivalent to travelling straight ahead without being pushed by anything else. On a flat sheet of paper, the straightest possible route between 2 points is an ordinary straight line. On the surface of a sphere, however, the equivalent path can look curved when viewed from outside the surface. Aircraft travelling long distances across Earth provide a familiar example. Their routes often appear curved on flat maps, even when they are following paths that make perfect sense on the globe itself. Spacetime curvature is far more subtle than the curvature of a surface, but the comparison captures something useful. An object can follow the straightest path available to it, even when that path appears curved from a broader perspective. Massive objects and light do not follow exactly the same kind of geodesic. An object with rest mass, such as a planet, spacecraft or person in freefall, follows what physicists call a time-like geodesic. A photon follows a null geodesic. The word null comes from the special spacetime interval associated with the path of light. The mathematical details are not essential here. The important point is that null geodesics are the paths available to anything travelling locally at the speed of light. So when a photon passes near a massive object and its path bends. General relativity does not require us to imagine some mysterious sideways force reaching out and grabbing the photon. The photon is following a null geodesic through curved spacetime. Locally, over a sufficiently small region, its motion can still be described as perfectly straight. Step back and examine a much larger region, however, and the trajectory can curve dramatically. This is why gravitational lensing works. Imagine a distant galaxy shining far beyond another massive galaxy lying between it and Earth. Light leaving the distant galaxy travels through spacetime that has been curved by the mass and energy of the foreground galaxy. Different light rays can follow different null geodesics around that foreground object. Some may pass one side. Others may travel around the opposite side. Both can eventually arrive at Earth. The observer may then see more than one image of the same distant source. If the alignment is especially neat, the light can be stretched into arcs. With a source, lens and observer positioned almost perfectly along the same line, the image may become a luminous circle known as an Einstein ring. Galaxy clusters can produce even more spectacular examples because they contain enormous amounts of matter spread across vast regions of space. Their gravitational fields can magnify galaxies lying billions of light years farther away, allowing astronomers to study objects that might otherwise be too faint to detect. All of this is light responding to geometry, but curved spacetime does more than decide whether a beam bends slightly to the left or right. It also determines which events can influence which other events. That is where the idea becomes especially important for black holes. In relativity, the future is not simply an unlimited collection of directions in which anything can happen. The speed of light places boundaries on cause and effect. A signal sent from one place can influence only regions it has enough time to reach without travelling faster than light. Because gravity changes spacetime geometry, gravity also changes these causal relationships. Near an ordinary star, the effect is modest. Light rays bend. Clocks at different gravitational potentials can run at slightly different rates, and the paths of freely falling objects differ from those they would follow in flat spacetime. But the general structure still allows outward travelling light to continue into the wider universe. A photon emitted from the surface of the Sun can climb away. Its frequency may shift slightly as it moves through the Sun's gravitational field, and its route may be affected by surrounding matter, but there is still a perfectly valid future path leading outward. A black hole represents something far more extreme. If enough mass and energy become concentrated within a sufficiently compact region, spacetime can become curved so strongly that the possible future paths themselves develop a boundary. The distinction is important. A star can bend light. A black hole can create a region from which no future-directed null geodesic reaches the distant outside universe. That is a much stronger statement. It means black holes are not merely objects with exceptionally powerful gravitational attraction. They possess a radically different causal structure. The same physics that produces a small deflection of starlight beside the Sun can, under sufficiently extreme conditions, reshape spacetime until the available paths of light no longer include an escape route. The photon does not lose its speed. It does not gain mass. It does not stop obeying the laws of relativity. Quite the opposite. It follows those laws exactly. The extraordinary part is that the geometry through which it travels has changed so profoundly that the straightest possible path through spacetime may no longer lead outward at all. Only a few months after Albert Einstein completed the general theory of relativity, another physicist found something remarkable hidden inside its equations. His name was Karl Schwarzschild. In 1916, while serving in the German army during the First World War, Karl Schwarzschild discovered an exact solution to Albert Einstein's field equations. His solution described the spacetime outside an idealized object that was perfectly spherical, not rotating, and electrically neutral. Those assumptions make the object simpler than most real astronomical bodies. But the mathematics revealed something profound. There was a particular distance from the centre, where the geometry of spacetime behaved in a completely new way. That distance is now called the Schwarzschild radius. Written in words, it is twice the gravitational constant multiplied by the mass and divided by the speed of light squared. The important feature is that the Schwarzschild radius depends directly on mass. The more massive the object, the larger this critical radius becomes. For every amount of mass equal to the mass of the Sun, the Schwarzschild radius is roughly 3 kilometers. So if an object had 10 times the mass of the Sun, its Schwarzschild radius would be roughly 30 kilometers. That is an extraordinarily small region in which to place so much matter. The Sun itself has a radius of roughly 700,000 kilometers. If the Sun could somehow be compressed while keeping the same mass, it would have to shrink from a sphere hundreds of thousands of kilometers across to one only a few kilometers in radius before its surface reached its Schwarzschild radius. For a star containing 10 solar masses, the equivalent scale would be only around 30 kilometers. This gives some sense of just how extreme black hole formation really is. It is not enough simply to have a large amount of mass. That mass must become extraordinarily compact. For sufficiently massive stars, gravitational collapse can eventually produce exactly these conditions after the star exhausts the nuclear fuel that had helped support it against its own gravity. The modern interpretation of the Schwarzschild radius is the location of the event horizon for an idealized Schwarzschild black hole. The phrase black hole itself arrived much later. During the 20th century, physicists gradually developed a clearer understanding of gravitational collapse and the strange objects predicted by general relativity. John Archibald Wheeler became particularly influential in popularizing the term black hole during the 1960s. It was a wonderfully simple name for an object whose mathematics could become anything but simple. The modern black hole, however, should not be confused with the earlier Newtonian idea of a dark star. A dark star was imagined as an object whose gravitational pull made escape difficult enough that light could not get away. The relativistic black hole is something deeper. Its defining boundary is built into the causal geometry of spacetime. The Schwarzschild radius is not a physical shell surrounding the black hole. There is no solid black surface there. There is no invisible membrane waiting to catch incoming photons. And there is no special substance at the horizon that absorbs light like black paint. An event horizon is a geometrically defined boundary. If you were falling toward a sufficiently large black hole, there would not necessarily be a local marker announcing that you had crossed it. No wall would rush toward you. No surface would suddenly appear beneath your feet. The significance of the horizon comes from what paths remain possible once it has been crossed. Outside the Schwarzschild radius, light can still travel outward along paths that eventually lead into the distant universe. A photon can be emitted away from the black hole and, if its trajectory is suitable, continue outward. At the horizon, the causal geometry reaches the critical boundary. Inside it, the situation changes fundamentally. The problem is no longer that light needs a little more speed. It already travels locally at the speed of light. The problem is that the outward paths themselves no longer lead outside. This is why the event horizon is such an unusual concept. Ordinary surfaces divide one material from another. The surface of Earth separates rock from atmosphere. The surface of a star marks a transition between the dense stellar interior and the surrounding space. An event horizon separates regions according to their possible causal futures. One side can still communicate with the wider universe, the other cannot. That means a photon does not need to strike anything in order to become trapped. It can cross the Schwarzschild radius while continuing to behave exactly as a photon should, following a null path through space-time at the local speed of light. Nothing physically grabs it at the boundary. Nothing suddenly makes it heavier. Yet after the crossing, every future directed route available to that photon remains inside the black hole. The Schwarzschild solution therefore provides the geometry behind one of the strangest features of black holes. The horizon is not a prison wall placed in space. It is a boundary created by spacetime itself. And to understand why even light cannot cross that boundary outward, the crucial question is not how powerful a force acts upon the photon. It is what directions the future still allows. One of the most common ways to explain a black hole is to say that its escape velocity reaches the speed of light. It is a useful idea. It is also not quite the whole story. In ordinary Newtonian physics, escape velocity has a very specific meaning. It is the minimum initial speed an object needs in order to move away from a gravitating body and continue outward indefinitely without receiving any further push. For Earth, that speed is roughly 11 kilometers per second at the surface. If you could throw something upward at exactly that speed, while ignoring the atmosphere and other complications, it would continue moving away from Earth without eventually falling back. The stronger the gravitational field, the larger the escape velocity becomes. For the Sun, the escape velocity from the visible surface is roughly 618 kilometers per second. Make an object more compact while keeping the same mass, and the escape velocity from its surface rises even further. This makes it tempting to imagine a black hole as the final step in that progression. Compress enough mass into a small enough region, and eventually the escape velocity reaches the speed of light. Since nothing can move faster than light, escape must then become impossible. As a first approximation, this sounds excellent. It even leads to the same characteristic radius that appears in the Schwarzschild solution. But the explanation becomes misleading if it is taken too literally. Escape velocity is not the same thing as the maximum speed an object is allowed to have while escaping. A rocket leaving Earth, for example, does not necessarily need to be travelling faster than 11 kilometers per second at every moment. If its engines continue providing thrust, it can climb gradually while remaining below the locally calculated escape velocity. The traditional escape velocity assumes that the object receives its initial push and then coasts upward without further propulsion. That assumption already makes it a slightly awkward way to describe a black hole. Suppose we try to apply the same picture to light. We might imagine a photon being launched outward from the event horizon, gravity pulling against it, and the photon gradually losing speed until it finally stops and falls back. That does not happen. A photon does not slow down locally in vacuum. A nearby freely falling observer always measures light passing locally at the same invariant speed of light. That remains true close to a black hole. It remains true at the event horizon, and it remains true after the photon has crossed inside. The black hole does not win by reducing the photon to some slower speed. There is no moment when light is crawling outward at half its usual speed before gravity finally catches it. This is one reason the phrase escape velocity can hide the deeper physics. A black hole is not simply an object with such a powerful pull that even the fastest possible traveller lacks enough speed. The defining feature of the event horizon is causal. An event occurring inside the horizon cannot send a signal to a sufficiently distant observer outside the black hole. It does not matter whether that signal is carried by a photon. It does not matter whether someone imagines a tremendously powerful rocket. It does not matter whether the signal is transmitted by any other physical process allowed by relativity. Once the event lies inside the horizon, the causal structure of spacetime prevents communication with a distant exterior. That is a stronger statement than saying the escape velocity is too high. The distinction can be seen by thinking about direction rather than speed. Outside a black hole, a photon aimed outward can still move toward larger and larger distances. The geometry permits such a future. Closer to the horizon, the range of directions that lead successfully outward becomes more restricted. At the horizon itself, the situation reaches a critical boundary, and once inside, every future directed path available to light remains within the black hole. The photon can still be travelling locally at the speed of light. It can still be aimed in what a nearby observer regards as the outward direction, yet its future does not lead back into the external universe. This sounds contradictory only if we imagine space near the black hole as behaving like ordinary space with an unusually strong force added on top. General relativity does not describe it that way. The geometry itself has changed. The escape velocity explanation therefore survives as a useful piece of intuition. It reminds us that increasing compactness makes escape progressively harder. It gives the correct scale for the Schwarzschild radius, and it provides a gentle bridge from familiar gravitational physics towards something more extreme. But it should not be mistaken for the fundamental reason light is trapped. Light is not defeated in a race, it is not too slow, and it does not require one final burst of acceleration that physics refuses to provide. The deeper explanation is that the event horizon marks a boundary in what can still causally influence the outside universe. To see that clearly, physicists use a concept called the light cone. A light cone describes the possible directions that light, matter, and information can take through spacetime. Far from a black hole, those possible future directions look reassuringly familiar. Near the horizon, they begin to tilt. Inside it, the picture changes completely, and once those future directions all point deeper inward, the mystery of why light cannot escape stops being a question about speed. It becomes a question about where the future is allowed to go. A useful way to understand why light cannot escape from inside a black hole is to stop thinking about gravity as a tug, and instead think about the structure of possible futures. Physicists often represent those possibilities using something called a light cone. A light cone is a way of showing which events in spacetime can influence which other events. The basic idea comes from one simple rule. No physical signal can travel locally faster than light. If you switch on a lamp, the light does not illuminate the entire universe instantly. The influence of that event spreads outward at the speed of light. Anything moving more slowly than light must remain within the region that the light can reach. That region defines the boundaries of cause and effect. Imagine yourself standing somewhere in relatively empty space. At this moment, there are many things you could do. You could move forward. You could turn around. You could remain almost where you are. You could send a beam of light in one direction or another. All of these choices belong to your future, but relativity places a limit on how quickly you can move from your present location to somewhere else. Light traces the outer boundary of what is physically reachable. This produces what is called a future light cone. The future light cone contains all the events you could potentially influence after this moment without requiring anything to travel faster than light. There is also a past light cone. That represents all the events that could have sent light, matter, or information to your current location. Looking into the night sky is, in a very literal sense, looking down portions of your past light cone. The light from the moon takes a little over 1 second to reach Earth. Light from the sun takes roughly 8 minutes. Light from distant galaxies may have been travelling for billions of years. The farther away we look, the farther into the past we see. Far from a black hole, light cones behave in a reassuringly ordinary way. A photon sent outward can continue toward greater distances, Another photon can travel inward. A spacecraft moving more slowly than light can choose from a range of directions between those extremes. The future contains many possible routes. As the black hole is approached, however, the geometry of spacetime becomes increasingly curved. The light cones change with it. This is sometimes described visually as the cones beginning to tilt inward. That language should not be taken to mean there are literal cone-shaped objects floating through space. A light cone is a representation of the causal directions allowed by spacetime, but the image is useful. Far away, one edge of the future light cone can point outward and the other inward. Move closer to the event horizon, and the range of future-directed paths that genuinely lead away from the black hole becomes narrower. The distinction between moving outward and eventually escaping becomes less straightforward. At the event horizon of an idealized non-rotating black hole, something very special happens. Consider a photon directed outward exactly at the horizon. In the stationary Schwarzschild geometry, the outward null path lies along the horizon itself. It does not climb away to larger and larger distances. The event horizon is itself generated by light-like paths. This already tells us that the horizon is not an ordinary location. Trying to hover exactly there would not solve the problem. To remain fixed just outside a black hole requires acceleration. The closer a stationary observer tries to hover to the horizon, the larger the required acceleration becomes. At the horizon itself, the required acceleration would become unbounded. No physical rocket could provide it. Now move just inside the horizon. The causal picture changes completely. Every future directed time-like or light-like path leads towards smaller values of the radial coordinate. That includes massive objects. It includes radio signals. It includes beams of light. And it includes a photon locally emitted in what an infalling observer would naturally describe as the outward direction. The photon still moves locally at the speed of light. Nothing has gone wrong with light. Nothing has reduced its speed. The difficulty is that the photon's future-directed null path no longer leads toward the external universe. This is where ordinary spatial intuition becomes unreliable. We tend to imagine that if an object can point outward and move fast enough, it must be able to increase its distance from the center. Inside the horizon, the geometry of spacetime does not preserve that familiar possibility. In the Schwarzschild description, moving towards smaller radial coordinate values becomes as unavoidable for future-directed motion as moving toward tomorrow is for us in ordinary life. You cannot escape Tuesday by running quickly enough on Monday. Inside a black hole, the comparison is not exact, but it captures something important. The inward direction is no longer merely one spatial choice among many. It has become tied to the future causal structure. This is the core of why a black hole can trap massless light. The photon does not fail because gravity needs mass and somehow finds some hidden amount inside it. The photon does not fail because the black hole slows it below the speed of light. And it does not fail because it runs out of energy halfway through an attempted escape. It fails because from inside the event horizon, there is no future directed causal path leading to the distant outside universe. Even the fastest possible signal already travels along the boundary of what causality permits. And if even that boundary points inward, nothing moving through spacetime can choose a more outward future. The event horizon therefore traps light in a far deeper sense than an ordinary barrier traps an object. A wall stops something from moving through space. A black hole changes which directions through spacetime still count as possible. The event horizon is often imagined as the most dramatic boundary in the universe. It sounds as though crossing it should feel like passing through some invisible wall, a place where gravity suddenly becomes overwhelming and the laws of physics change in an instant. For a sufficiently large black hole, that is not what an infalling observer would experience. At the event horizon itself, there may be nothing locally unusual to announce that the crossing has happened. No surface appears, no shockwave arrives, there is no flash marking the boundary, and there is no sudden moment when light stops behaving like light. This follows closely from Albert Einstein's equivalence principle. A freely falling observer, over a sufficiently small region of spacetime, experiences physics in much the same way as someone floating freely far from strong gravitational influences. If you were falling toward a very large black hole inside a small enclosed laboratory, local experiments might not reveal the exact moment when you crossed the event horizon. You would still see nearby light travelling normally. Objects beside you would continue falling alongside you. Your clock would continue ticking. The horizon is therefore very different from the surface of a planet or star. A planet has matter at its surface. A star has hot plasma. An event horizon is not made of anything. Now imagine a photon falling toward a black hole. As it approaches the horizon, the photon follows a null geodesic through curved spacetime. When it reaches the horizon, nothing collides with it. Nothing breaks it, nothing grabs it and drags it through. The photon simply continues along its path. A nearby freely falling observer would still measure that photon moving locally at the speed of light. And after crossing the horizon, the same remains true. The photon does not somehow notice that it has entered a black hole. In fact, speaking about what a photon itself experiences requires care, because a photon does not possess an ordinary rest frame. There is no valid viewpoint in which we can travel alongside the photon while it remains stationary, but we can describe what nearby freely falling observers measure. They see light behaving normally as it passes through their local region of spacetime. The event horizon is important for a completely different reason. Its significance is global. To know whether a particular event lies inside a black hole, we must ask about the future of signals leaving that event. Can any light ray beginning there eventually reach the distant external universe? If the answer is yes, the event lies outside the black hole. If every future directed light path remains trapped within the interior, the event lies inside. That means the event horizon cannot be identified merely by examining a tiny patch of space around it. Its definition depends on the larger causal structure of spacetime. This is one reason black holes can feel so unintuitive. Locally, the horizon may be uneventful. Globally, it marks a profound divide. Suppose an observer has already crossed it and switches on a torch aimed outward. The beam still leaves the torch at the locally measured speed of light. The observer has done nothing wrong. The torch is functioning perfectly. The photons are behaving perfectly. But those outward directed photons cannot return to the distant universe. Inside the horizon, even what the falling observer calls outward remains part of a future that is confined to the black hole. The path may initially point away from the centre in the observer's immediate local frame, but the complete null geodesic does not lead beyond the event horizon. There is no hidden reserve of speed that could solve the problem. Light is already moving as quickly as causality allows. This also reveals why the event horizon should not be confused with the singularity. In the idealized Schwarzschild solution, the horizon occurs at the Schwarzschild radius. The singularity lies deeper inside, at the center of the classical geometry. At the horizon, spacetime curvature can be perfectly finite. For a supermassive black hole, the tidal forces there may even be relatively gentle. The singularity is very different. Within classical general relativity, certain measures of spacetime curvature grow without bound as the central singularity is approached. That signals that the classical description has reached an extreme limit. Most physicists expect that a complete theory of quantum gravity would be required to understand what truly happens under such conditions. The horizon, then, is not where the known equations necessarily break down. It is where causal escape ends. During the 20th century, Roger Penrose helped reveal how deeply this behavior is built into general relativity. His work on gravitational collapse showed that singularities were not merely curiosities produced by perfectly symmetrical mathematical examples. The Penrose singularity theorem demonstrated that, under broad physical conditions, gravitational collapse can lead inevitably to geodesic incompleteness once a trapped surface forms and suitable assumptions are satisfied. This transformed the way physicists thought about black holes. Extreme gravitational collapse was not simply an artifact of choosing an unrealistically neat spherical star. The structure emerged naturally from the theory itself. And that brings us back to the quiet strangeness of crossing a horizon. Nothing needs to strike the photon. Nothing needs to make it massive. Nothing even needs to happen locally at the boundary that feels particularly dramatic. The photon simply continues forward at the speed of light. But after the crossing, forward no longer includes a route back to the outside universe. The event horizon does not announce itself with a wall. It announces itself through the future. Once that boundary has been crossed, every allowed future-directed path remains on the same side. From far away, falling into a black hole looks very different from the experience of the person or object doing the falling. Imagine watching a small glowing spacecraft descend toward a non-rotating black hole while you remain safely at a great distance. From the spacecraft's point of view, the journey can continue smoothly. Its onboard clock keeps ticking. It approaches the event horizon and, provided tidal forces are not too extreme, crosses it in a finite amount of its own time. But the light reaching you from that spacecraft tells a very different story. As the spacecraft moves deeper into the black hole's gravitational field, the signals it sends outward take longer and longer to reach you. This is connected to gravitational time dilation. In general relativity, clocks at different positions in a gravitational field do not necessarily accumulate time at the same rate when compared using a distant stationary reference. A clock held closer to a black hole appears to run more slowly when judged by an observer remaining farther away. If the spacecraft transmits one light pulse every second according to its own clock, those pulses do not necessarily arrive at your detector 1 second apart. As the craft approaches the event horizon, the interval between successive received signals grows. The spacecraft appears to slow. Its motions seem increasingly stretched out. But there is another effect happening at the same time. The light itself becomes gravitationally redshifted. A photon climbing outward from deep within a gravitational field is received far away with a lower frequency than it had when compared locally near its point of emission. Visible light shifts toward the red end of the spectrum. Push the effect far enough, and the radiation moves beyond visible red into infrared, then into still lower frequency bands. The energy carried by each received photon is also reduced, because photon energy depends on frequency. So the falling object does not merely appear slower, it also appears redder and dimmer. Imagine the spacecraft beginning as a bright white point. As it falls, its clock appears to slow. Its light becomes increasingly stretched to longer wavelengths. Its brightness fades. Eventually, the signals become so delayed, so redshifted, and so weak that a practical detector would stop seeing the spacecraft at all. This is more accurate than the popular image of an astronaut remaining forever as a perfectly visible frozen picture painted onto the horizon. The phrase frozen at the horizon comes from a particular way of describing the black hole using coordinates adapted to a stationary observer far away. In those Schwarzschild coordinates, the coordinate time assigned to reaching the event horizon grows without bound. That mathematical description is useful, but it does not mean the falling traveller physically stops. The traveller does not feel time freezing. Their heart does not stop beating at the boundary. Their wristwatch does not hesitate over one final second. From their own perspective, measured using what physicists call proper time, the horizon can be crossed normally and in a finite duration. The apparent freezing belongs to the distant description, and even from far away, what is actually observed is not a bright object sitting forever in one place. Every image you see arrives by photons. As the spacecraft approaches the horizon, fewer useful photons reach your detector over any convenient period of observation. Those that do arrive carry progressively less energy and are shifted to increasingly long wavelengths. Real telescopes have finite sensitivity. Real detectors collect finite numbers of photons. Eventually, the spacecraft simply fades beyond detectability. This distinction matters because seeing an object and describing what happens to the object are not the same thing. Astronomy is always based on delayed information. When you look at the sun, you see light that left it roughly 8 minutes earlier. When you observe another galaxy, you may be seeing it as it existed millions or billions of years ago. Near a black hole, this ordinary delay becomes extreme because spacetime itself strongly affects the path and frequency of the escaping light. The distant observer is therefore watching an increasingly delayed record of the infall. Meanwhile, according to the local physics of the falling object, the journey continues. General relativity contains no contradiction here. Different observers can assign very different coordinate descriptions to the same sequence of events while still agreeing on locally measurable physical quantities. The infalling traveller crosses the horizon in finite proper time. Light emitted ever closer to that crossing becomes increasingly difficult for the distant observer to receive, and light emitted after the crossing cannot reach that distant observer at all. This is why the horizon can seem almost ghost-like from far away. The falling object appears to slow toward it. Its light reddens, its image fades. Then it disappears, not because the traveller became physically frozen on the boundary, but because the information reaching the outside universe becomes ever more delayed and weakened until no new signal from beyond the horizon can arrive. What the distant observer sees is therefore not the traveller stopping. It is the final visible light from a region that is becoming causally disconnected from them. A black hole can do more than bend the path of light. Under very precise conditions, it can allow light to travel around it in a circle. For an idealized Schwarzschild black hole, meaning one that is spherical, non-rotating, and electrically neutral, there is a special region outside the event horizon known as the photon sphere. The name is slightly misleading if it makes us imagine a glowing shell made of trapped photons. The photon sphere is not a physical surface, and it is not normally filled with light orbiting neatly forever. Instead, it identifies a radius where circular paths for photons are mathematically possible. For a Schwarzschild black hole, the radius of the photon sphere is 3 times the gravitational constant multiplied by the black hole mass and divided by the speed of light squared. The Schwarzschild event horizon lies at twice the gravitational constant multiplied by the black hole mass and divided by the speed of light squared. So the photon sphere sits at 1.5 times the radius of the event horizon. Imagine, for example, a non-rotating black hole with 10 times the mass of the Sun. Its event horizon would have a radius of roughly 30 kilometers. The photon sphere would lie at roughly 45 kilometers from the center. That is remarkably close. At this radius, spacetime is curved so strongly that a photon travelling in exactly the right direction can follow a circular null geodesic around the black hole. It sounds almost as though the photon has become a tiny moon. But there is an important difference. These circular photon orbits are unstable. A planet can remain in a stable orbit for billions of years if its motion is arranged correctly. Earth, for example, can experience small disturbances without immediately falling into the Sun or being flung into interstellar space. A photon on the Schwarzschild photon sphere has no such comfortable margin. A tiny deviation from the exact circular trajectory changes the outcome, moves slightly toward the black hole, and the photon can spiral inward. Move slightly outward, and it can eventually escape. So although perfectly circular photon paths exist mathematically, nature does not provide them with much forgiveness. The photon sphere must also be kept separate from the event horizon. They are not the same boundary. At the photon sphere, escape is still possible. A photon produced there can travel outward and reach the distant universe if it begins along a suitable direction. Even photons passing close to the photon sphere can sometimes bend dramatically around the black hole and then escape. Inside the event horizon, by contrast, no future directed light path reaches the distant exterior. That distinction is fundamental. The photon sphere is a region of extreme light bending. The event horizon is a causal boundary. The behavior near the photon sphere produces some of the strangest optical effects associated with black holes. A ray of light approaching from far away may pass comfortably outside this region and be deflected only modestly. Another ray passing closer can bend through a much larger angle, fine-tune its path still further, and the light may sweep around a substantial fraction of the black hole before heading outward again. Some trajectories can loop around the black hole one or more times before finally escaping. Each additional loop requires increasingly precise conditions, but the result is an intricate collection of possible images. Light from the same source can reach an observer along several different paths. Some rays take relatively direct routes, others travel around the black hole before arriving. This produces multiple gravitationally lensed images with increasingly faint and compressed features associated with photons that pass extremely close to the critical region. The black hole is effectively rearranging the routes through which information can reach the observer. There is another useful way to think about this behavior. Imagine a source of light positioned outside the event horizon. At a comfortable distance from the black hole, it can emit photons in many outward directions, and a broad range of them can eventually travel far away. As the source is moved deeper into the gravitational field, closer to the horizon, the range of emission directions that lead to escape becomes increasingly restricted. This range is often described as an escape cone. Photons launched within the appropriate cone can still reach distant regions. Photons launched outside it may be bent inward and captured. Closer to the horizon, the escape cone narrows dramatically for a stationary source. Fewer directions lead successfully to infinity. At the event horizon, the distinction reaches its limit, and once the emission point lies inside the horizon, there is no escape cone leading to the outside universe at all. This gives a particularly clear picture of how curved spacetime controls massless light. The black hole does not alter the photon by giving it mass. It does not reduce the photon's local speed. And it does not need to place anything physically in the photon's way. Instead, it changes the set of trajectories available. Far from the black hole, there are many routes outward. Near the photon sphere, some of those routes can twist almost unbelievably around the black hole before escaping. Closer to the horizon, successful routes become fewer, and inside the horizon, they disappear entirely. The photon sphere therefore reveals the transition between ordinary gravitational bending and the much more extreme causal trapping associated with the event horizon. Light can skim, it can bend, it can loop around the black hole. Under perfectly arranged conditions, it can even orbit. Yet throughout all of this, the photon remains massless. The astonishing behaviour belongs not to some change within the light itself, but to the geometry of the spacetime through which that light is trying to travel. A black hole has no solid surface, and yet when astronomers image one, they can still see something that looks remarkably like a dark silhouette. That dark region is often called the black hole's shadow. The name is useful, but it can give the wrong impression if we imagine that astronomers are directly photographing the event horizon as though it were the surface of a dark planet. They are not. The shadow appears because certain paths that light could have followed toward the observer are instead diverted into the black hole. If a photon crosses the event horizon, it no longer has any future directed route back to the outside universe. From the point of view of a distant telescope, that means some directions on the sky simply fail to deliver the light that might otherwise have arrived. The result is a dark region surrounded by much brighter emission. Most black holes in the universe are not sitting alone in perfectly empty space. Gas, dust and plasma can orbit around them. As that material falls inward, gravitational energy is converted into heat and motion. The plasma can become extraordinarily hot, with charged particles spiraling through magnetic fields and producing electromagnetic radiation. In some systems, the region around a black hole can become one of the brightest environments in the universe. The black hole itself remains dark. The surrounding material does not. This creates a rather beautiful contrast. Bright plasma moves around an object that emits no ordinary light of its own, while the black hole's gravity bends the radiation travelling through the surrounding spacetime. Some photons leave the plasma and travel fairly directly toward us. Others pass close to the black hole and are strongly deflected. Light emitted from material on the far side can even curve around the black hole before reaching the observer, meaning we can receive radiation from regions that would have been hidden if light simply travelled in straight lines through flat space. This is gravitational lensing operating in one of its most extreme forms. The apparent dark shadow created by the black hole is also larger than the event horizon itself. That distinction is important. The event horizon is the causal boundary beyond which no light can escape. The shadow seen by a distant observer is determined by which photon trajectories are captured, and which can still reach the telescope. Near the photon region, light paths are bent so strongly that a tiny difference in direction can decide whether a photon escapes or disappears into the black hole. The critical set of these trajectories creates the apparent edge of the shadow. For an idealized Schwarzschild black hole viewed against a bright background, the radius of this critical shadow is roughly 2.6 times the Schwarzschild radius. So the dark patch in an image does not directly trace the physical location of the event horizon. It reflects the larger region of extreme light bending surrounding it. This distinction became especially famous in 2019. The Event Horizon Telescope collaboration released the first image showing the shadow of a supermassive black hole. The object lies at the centre of the giant elliptical galaxy Messier 87, roughly 55 million light-years from Earth. Its mass is several billion times the mass of the Sun. The image showed a bright, roughly ring-shaped structure surrounding a dark central region. It immediately became one of the most recognizable astronomical images ever produced. But the Event Horizon Telescope is not a single telescope sitting on one mount. The collaboration combines radio observatories spread across Earth and uses a technique called very long baseline interferometry. By coordinating observations from widely separated locations, the system can achieve an angular resolution comparable to that of a telescope with a size approaching the diameter of Earth. The observations were made at a wavelength of about 1.3 millimeters in the radio portion of the electromagnetic spectrum. What the telescopes detected was radiation from extremely hot plasma surrounding the black hole. They were not detecting light coming from inside the event horizon. No ordinary photon emitted beneath that boundary could travel outward and reach Earth. Instead, the observed ring is produced by a combination of emission from surrounding material, relativistic motion, magnetic processes, and the severe bending of photon paths in the black hole's gravitational field. The darker centre appears because many trajectories aim toward that part of the image end at the black hole, rather than connecting the emitting plasma to us. A few years later, in 2022, the Event Horizon Telescope collaboration released another remarkable result. This time, the target was Sagittarius A star, the compact object at the centre of our own Milky Way galaxy. Sagittarius A star has a mass of roughly 4 million times that of the Sun. It is vastly less massive than the black hole in Messier 87, which means the physical scales around it are much smaller and the surrounding plasma changes much more rapidly. That made the observations particularly difficult. While the supermassive black hole in Messier 87 changes comparatively slowly, material close to Sagittarius A star can evolve over timescales of minutes. It is a little like trying to take a long exposure photograph of something that refuses to sit still. Even so, the reconstructed image again revealed a bright ring surrounding a darker central region with a size broadly consistent with predictions from general relativity. These images provide a striking visual example of what it means for spacetime to control light. The darkness is not created by a solid black surface absorbing photons. There is no crust beneath the glowing plasma. No shell surrounds the black hole, waiting to block the view. The photons are responding to geometry. Some null geodesics lead from the surrounding plasma to the distant telescope. Some wind around the black hole before arriving. Some approach the critical photon region and become dramatically deflected. Others cross the event horizon and are permanently removed from the set of signals that can reach us. The shadow is therefore a map of missing light. It is the visual consequence of certain paths through spacetime having no connection back to the observer, and that makes these images especially relevant to the strange question of massless light. Nothing in the image requires photons to gain rest mass. Nothing requires the black hole to physically grab them. The dark centre exists because curved spacetime determines where those photons are allowed to go. Some paths still lead across millions of light years and eventually reach a radio telescope on Earth. Others lead inward. And once those paths cross the horizon, the universe outside simply stops receiving their light. The simplest black hole is a useful place to begin, but nature rarely seems interested in keeping things quite that tidy. The Schwarzschild black hole is perfectly spherical, completely non-rotating, and electrically neutral. It is an elegant solution to Albert Einstein's general theory of relativity, but real black holes are expected to rotate. That is because the stars and gas that form black holes are usually rotating already. When a massive star collapses, its angular momentum does not simply disappear. As the material contracts into a much smaller region, the rotation can become increasingly important, rather like a spinning ice skater rotating more quickly when drawing their arms inward. The more realistic description, therefore, requires a different geometry. In 1963, Roy Patrick Kerr discovered an exact solution to Albert Einstein's field equations describing a rotating, electrically neutral black hole. The resulting object is known as a Kerr black hole. For astrophysical black holes, Kerr geometry is generally much more relevant than the perfectly non-rotating Schwarzschild case. Rotation changes the surrounding spacetime in a remarkable way. A rotating black hole does not merely sit inside spacetime while spinning like a ball. Its rotation affects the geometry around it. This effect is known as frame dragging. In simple terms, rotating mass can drag the local inertial structure of spacetime around with it. The effect is extremely small around ordinary rotating objects such as Earth, but near a rapidly spinning black hole it can become dramatic. Imagine spacetime around the black hole being twisted slightly in the direction of rotation. This is only an analogy because spacetime is not literally a fluid being stirred, but it helps capture the idea. Matter and light travelling nearby must follow paths through this rotating geometry. As a result, the black hole spin influences which trajectories are possible. One of the most unusual consequences is a region called the ergosphere. The ergosphere lies outside the event horizon of a rotating black hole, although its exact shape differs from the horizon beneath it. Within this region, frame dragging becomes so strong that remaining stationary relative to distant stars is impossible. Everything must move, at least to some degree, in the direction of the black hole's rotation. A spacecraft could fire its engines as hard as it liked, and still could not simply hover there while maintaining a fixed angular position relative to the distant universe. Spacetime itself has constrained the available future directed paths. But the ergosphere is not the same thing as the event horizon. That distinction matters. An object inside the ergosphere can still escape the black hole if it follows a suitable trajectory. Light can also leave from portions of the ergosphere. Cross the event horizon, however, an escape to the distant outside universe is no longer possible. So the ergosphere is a region where remaining stationary becomes impossible. The event horizon is the boundary beyond which causal escape becomes impossible. Rotation also changes the paths available to photons. Around a non-rotating Schwarzschild black hole, there is a simple photon sphere at a particular radius where circular photon orbits are possible. Around a Kerr black hole, the situation becomes more complicated. There is no single simple spherical surface describing all possible photon motion. Instead, there is a broader photon region containing different possible null trajectories. The black hole's spin matters because photons travelling with the direction of rotation behave differently from photons travelling against it. A photon moving in the same direction as the spin can orbit closer to the black hole than one moving in the opposite direction. Frame dragging effectively changes the geometry experienced by each trajectory. This means that the distinction between prograde motion moving with the spin and retrograde motion moving against it becomes physically important. The same asymmetry appears in the motion of matter. Around a non-rotating black hole, the innermost stable circular orbit for ordinary matter lies at a particular radius determined by the mass of the black hole. For a rotating black hole, that radius depends strongly on direction. Matter orbiting in the same direction as a rapidly spinning black hole can remain in stable circular motion much closer to the event horizon. Matter moving against the rotation must remain farther away if the orbit is to stay stable. This affects the accretion disk surrounding real black holes. Gas orbiting closer to the black hole can release more gravitational energy before plunging inward, which means the black hole's spin can influence how efficiently the surrounding material produces radiation. Rotation also changes gravitational lensing. Light passing one side of the black hole does not necessarily follow the mirror image of light passing the opposite side. The twisting of spacetime changes the available null geodesics. Some rays can be dragged farther around the black hole, others are deflected differently depending on whether they move with or against the spin. The apparent black hole shadow can therefore become asymmetric. For many viewing angles, the overall shape remains remarkably close to circular, but its brightness distribution and detailed structure can reveal the influence of rotation, orbital motion, and relativistic beaming in the surrounding plasma. This is one reason observations of black hole environments can contain information about spin. Astronomers can examine radiation from accretion disks, the motion of nearby matter, the structure of jets, and the behavior of strongly bent light in an attempt to infer how rapidly a black hole is rotating. Through all of this complexity, however, the central lesson about light remains unchanged. Photons do not need rest mass in order to be affected. A Kerr black hole does not somehow give light mass so that frame dragging can pull it around. The photon remains massless. It continues to travel locally at the speed of light. What changes is the geometry. The rotating black hole alters the spacetime through which the photon must move. That geometry determines the null trajectories available to it. Some lead outward, some loop around the black hole, some are strongly distorted by frame dragging, and some cross the event horizon and never reconnect with the outside universe. Rotation therefore makes the paths of light stranger, but it does not change the basic reason those paths behave strangely. The black hole is still not grabbing the photon as though it were an ordinary massive object. The massless photon is simply following the light-like routes that curved and rotating spacetime allows. Saying that light has no rest mass can easily create the impression that light should somehow sit outside gravity. But general relativity does not treat rest mass as the only source of gravitational effects. That is one of the most important differences between Albert Einstein's description of gravity and the simpler picture that came before it. In general relativity, the curvature of spacetime is connected to the complete physical content of matter and fields. Rest mass matters, but so does energy. So does momentum. Pressure matters as well, along with stresses such as tension and the flow of energy from one place to another. Physicists collect these quantities into what is called the stress-energy tensor. The name sounds rather formidable, but the basic idea is manageable. The stress-energy tensor is a mathematical description of how energy, momentum, pressure and stress are distributed through spacetime. Albert Einstein's field equations connect this distribution to the curvature of spacetime. So when physicists say that matter tells spacetime how to curve, the word matter is really shorthand for something broader. Energy and momentum are part of the story too. This becomes important when thinking about photons. A photon has zero rest mass, but it carries energy. It also carries momentum. That means light is not gravitationally irrelevant. A simple thought experiment helps make this clearer. Imagine a perfectly sealed box floating somewhere in space. First, consider the box while it is empty. Now imagine placing electromagnetic radiation inside it, so that photons are bouncing between the walls. The box now contains more total energy than it did before. Nothing about the photons requires them to possess rest mass individually. Yet the total energy of the complete system has increased. According to relativity, that additional energy contributes to the gravitational properties of the box. The radiation adds to the total mass energy of the system. If enough energy were somehow stored inside, the difference would not merely be philosophical. It would affect how the system responds gravitationally and how it contributes to spacetime curvature. The same principle appears whenever light transfers momentum. Photons striking a mirror exert radiation pressure. Photons absorbed by atoms can change their motion. Radiation from stars can push dust grains through interstellar space. Solar sails can use the momentum carried by sunlight to produce a gentle but continuous force. All of these effects remind us that massless does not mean without physical influence. Light participates in gravitational physics in two closely related ways. First, curved spacetime affects the paths followed by photons. That is why light bends around stars and galaxies, and why black holes can redirect or capture photon trajectories. Second, the energy and momentum carried by electromagnetic radiation contribute to the physical content that affects spacetime geometry. Light, therefore, does not merely respond to gravity. In principle, light also helps produce gravitational effects. Usually that contribution is tiny compared with the influence of stars, planets, or other concentrations of matter. But there have been periods in cosmic history when radiation was enormously important. The early universe provides a striking example. Today, the energy density of ordinary radiation is small compared with the dominant forms of cosmic energy associated with matter and dark energy. Travel far enough back in cosmic history, however, and the situation changes. As the universe expands, radiation becomes increasingly diluted. Its photons also lose energy through cosmological redshift, as their wavelengths are stretched by the expansion of space. Matter thins out as the universe expands as well, but radiation energy density falls more rapidly. Reverse the expansion and look backward in time, and radiation becomes important faster than matter does. During the early universe, there was a long radiation-dominated era in which photons and other highly relativistic particles made a major contribution to the total cosmic energy density. That energy affected the expansion rate of the universe. It influenced how quickly the universe cooled. It helped determine the conditions in which particles, atomic nuclei, and eventually atoms could form. So the gravitational significance of radiation is not some tiny correction that exists only on paper. At certain stages of cosmic history, it was central to the behavior of the universe itself. This helps untangle an important piece of the black hole puzzle. When someone hears that gravity is produced by mass, it is natural to ask how a massless photon could possibly be affected. But the premise is already too narrow. General relativity does not say that gravity acts only on rest mass. The geometry of spacetime is connected to energy, momentum, pressure, and stress. Photons carry energy and momentum. They therefore belong completely within the gravitational description. At the same time, a photon near a black hole does not need to possess rest mass before the curved geometry can determine its path. The photon simply travels along the null route permitted by spacetime. If that route bends around a star, the photon bends. If it loops near a black hole, it loops. If it crosses an event horizon, its future remains inside. Nothing about this requires hidden mass. Nothing requires light to stop being light. The statement that a photon has zero rest mass is entirely correct. The statement that light, therefore, has nothing to do with gravity is not. Light carries energy. Light carries momentum. Light follows curved spacetime. And even light contributes, however slightly in most situations, to the curvature that gravity describes. A massless photon is not outside gravity. It is woven into the same relativistic structure as everything else in the universe. One of the easiest mistakes to make when thinking about black holes is to imagine that gravity somehow slows light down. The picture seems natural. A photon tries to move outward, gravity pulls against it, the photon gets slower and slower, and eventually, at the event horizon, it simply stops. But that is not what general relativity says. Locally, light in a vacuum always travels at the speed of light. That remains true far from a black hole. It remains true close to the event horizon. And it remains true inside the event horizon. A nearby freely falling observer measuring a passing photon would still find that light moving at the same invariant speed as anywhere else in vacuum. The black hole does not gradually reduce that local speed. What can change is the way motion looks when described using coordinates chosen by an observer far away. Coordinates are essentially a system for assigning positions and times to events. In ordinary situations, different sensible coordinate systems usually tell stories that look broadly familiar. Near a black hole, that can stop being true. The usual Schwarzschild coordinates are designed around observers who remain stationary outside a non-rotating black hole. When those coordinates are extended toward the event horizon, outward and inward light rays can appear to behave in peculiar ways. The coordinate speed assigned to outgoing light can approach 0 at the horizon. That sounds dramatic. But a coordinate speed is not automatically the same thing as a speed measured locally by someone passing through that region. This distinction is vital. A map can make Greenland look enormous without physically stretching Greenland. In a similar spirit, coordinates can distort the way motion is represented without changing what a local observer actually measures. At the event horizon, Schwarzschild coordinates become particularly awkward. Other coordinate systems can describe the same horizon smoothly, with an infalling object passing through without encountering any mathematical breakdown. The physics has not changed, only the bookkeeping has. So imagine a photon falling inward toward the black hole. It reaches the event horizon and crosses it. A nearby freely falling observer still measures that photon travelling locally at the speed of light. There is no sudden loss of velocity. There is no moment when the photon starts dragging itself through spacetime like someone walking through deep mud. Now imagine a photon inside the horizon that is emitted locally in what an infalling observer would call the outward direction. That photon also travels locally at the speed of light. Yet it still cannot reach the external universe. This is the part that feels most contradictory. How can something move outward at the fastest possible speed and still fail to escape? The answer is that inside the horizon, the geometry of spacetime has changed the meaning of the possible future paths. A useful, though imperfect, analogy is to imagine a network of roads. Far from the black hole, some roads lead inward and others lead outward. Closer to the horizon, the roads that genuinely lead away become fewer. Inside the horizon, every future directed road ultimately leads deeper into the black hole. You can drive as quickly as the laws allow. You can point along the most outward route available. But there is no road connecting your location to the distant outside universe. The analogy has limits. Spacetime is not a substance flowing inward like water. Photons are not leaves being swept along by a current. There is no invisible river physically carrying them toward the centre. The deeper statement is geometric. The allowed light-like paths through spacetime remain confined inside the horizon. This also explains why adding more engine power would not rescue a spacecraft. A massive spacecraft cannot travel locally at the speed of light. Its possible future motions must remain inside its local light cone. Light itself forms the boundary of that cone. So a photon already has access to the most extreme causal trajectories allowed by relativity. A massive traveller has fewer options, not more. Fire the engines harder and the spacecraft can change its local motion. It can accelerate, it can choose different time-like paths. But every physically allowed future path still remains inside the light cone. And inside the event horizon, that entire future light cone is oriented so that no causal path reconnects with the exterior. To escape would therefore require something more radical than simply moving faster. It would require a trajectory outside the allowed local light cone. In physical terms, that would mean faster than light causal propagation. General relativity does not permit ordinary matter, light, or information to do that. This is why saying that even light cannot escape is slightly misleading if it makes us imagine light trying and failing because it is not fast enough. Light is already travelling at the universal limit. There is no extra speed left to add. The black hole wins in a completely different way. It changes the causal geometry so that speed is no longer the deciding issue. A photon inside the horizon does exactly what a photon is supposed to do. It travels locally at the speed of light. It follows a null path through spacetime. Nothing slows it. Nothing makes it heavy. Nothing breaks the laws of relativity. And yet every future directed path available to it remains within the black hole. The light has not lost its speed. It has lost the possibility of an outward future. At first, Hawking radiation seems to create an awkward problem. If nothing can escape from inside a black hole, then how can a black hole emit anything at all? The answer is that Hawking radiation is not ordinary light climbing out from beneath the event horizon. That distinction is essential. In classical general relativity, once a photon is inside the event horizon, there is no future directed path that carries it back to the distant outside universe. Hawking radiation does not overturn that rule by somehow allowing photons to sneak across the boundary in the wrong direction. Instead, the effect appears when quantum theory is applied to fields in curved spacetime. In 1974, Stephen William Hawking showed that a black hole is not completely black when quantum fields are taken seriously. To a distant observer, a black hole can emit radiation with an approximately thermal spectrum. This was a remarkable result, because classical black holes had previously been understood as perfect absorbers. Quantum theory changed the picture. A common explanation says that pairs of particles constantly appear near the event horizon. One falls into the black hole while the other escapes, becoming Hawking radiation. That image is easy to remember, but it should not be taken too literally. Hawking's calculation does not require a physical pair of particles to pop into existence at one precise point beside the horizon, with one member of the pair beginning inside and then somehow providing the escaping radiation. The real explanation is more subtle. Quantum field theory does not treat particles as the deepest underlying objects. Fields come first. What counts as a particle can depend on how those fields are observed, especially in curved spacetime, where the geometry changes the relationship between different regions and different observers. A state that may be described one way near a black hole can correspond to a flux of particles when measured by an observer far away. The event horizon and the surrounding curved geometry alter the quantum field modes in such a way that the distant observer detects approximately thermal radiation. No ordinary photon needs to travel outward from deep inside the black hole. The radiation is associated with quantum fields in the spacetime surrounding the black hole and with the global structure of that spacetime. This is why Hawking radiation does not contradict the event horizon. It belongs to a quantum description that is richer than the simple classical picture. The temperature of Hawking radiation depends strongly on the mass of the black hole. In fact, the relationship runs in the opposite direction from what everyday intuition might suggest. Larger black holes are colder. Smaller black holes are hotter. The Hawking temperature is inversely proportional to the black hole's mass. A black hole with roughly the mass of the Sun has a Hawking temperature of only around 6 times 10 to the minus 8 Kelvin, or several tens of billionths of a Kelvin above absolute zero. That is extraordinarily cold. The cosmic microwave background that fills the universe today has a temperature of roughly 2.7 Kelvin, so a solar mass black hole is far colder than the radiation already surrounding it. At the present age of the universe, such a black hole would absorb more energy from its environment than it would lose through Hawking radiation. Supermassive black holes are colder still. A black hole millions or billions of times the mass of the Sun has an even lower Hawking temperature. For these enormous objects, evaporation is unimaginably slow. But in a sufficiently empty and cold future universe, the balance could eventually reverse. If the surrounding radiation became colder than the black hole could lose more energy through Hawking radiation than it gained from its environment. As energy leaves, the black hole's mass decreases. As the mass decreases, the Hawking temperature rises. The black hole then radiates more strongly. This means evaporation accelerates as the black hole becomes smaller. For an isolated black hole with the mass of the Sun, the total evaporation time is vastly longer than the current age of the universe, on the order of about 10 to the 67 years. Supermassive black holes would survive for even longer. Hawking radiation, therefore, does not mean that astrophysical black holes are rapidly glowing themselves away. For all practical human timescales, their quantum evaporation is almost absurdly slow. But conceptually, the discovery was enormous. It connected 3 areas of physics that had previously seemed very different. General relativity describes gravity and spacetime. Quantum theory describes fields and particles. Thermodynamics describes temperature, entropy, and heat. Black holes turned out to sit directly at the intersection of all 3. This connection had already begun to emerge through the work of Jacob David Bekenstein, who argued that black holes should possess entropy related to the area of their event horizons. Stephen William Hawking's calculation gave that thermodynamic picture a physical temperature and a real radiation process. From there, an even deeper problem appeared. If a black hole forms from matter carrying detailed quantum information and then eventually evaporates into apparently thermal radiation, what happens to that information? This became known as the black hole information problem. It remains one of the central puzzles linking quantum theory and gravity. The full solution is still tied to the unfinished search for a consistent theory of quantum gravity. But none of this changes the classical answer to why light cannot escape once it is inside an event horizon. Hawking radiation is not a photon beginning beneath the horizon and fighting its way outward. It is not evidence that the event horizon occasionally becomes porous, and it does not mean that light secretly has enough speed to escape after all. The classical causal boundary remains intact. What Hawking radiation tells us is something subtler. A black hole placed inside a quantum universe cannot be understood using classical geometry alone. Quantum fields respond to curved spacetime in ways that produce radiation for distant observers. The black hole can therefore slowly lose energy without ordinary particles simply travelling backward through the event horizon. So when we say that nothing escapes a black hole, the statement still holds in the classical sense that matters for a photon already inside. Hawking radiation does not provide that trapped photon with a hidden exit. Instead, it reveals that the space surrounding the horizon is governed not only by gravity, but also by quantum fields. And when those two descriptions meet, even something called a black hole turns out not to be perfectly black. Black holes are not merely mathematical ideas sitting quietly inside equations. They leave fingerprints all across the universe. We cannot place a detector beneath an event horizon and send the results back out. By definition, no ordinary signal from inside that boundary can reach the distant exterior. So the evidence for black holes comes from something subtler. We watch what they do to everything around them. One of the clearest examples lies at the centre of our own Milky Way galaxy. There, in the direction of the constellation Sagittarius, sits a compact radio source known as Sagittarius A star. For decades, astronomers have tracked stars moving around this apparently dark central region. Two research programs became especially important, associated with Reinhard Genzel and Andrea Mia-Ghez. Using powerful infrared telescopes and increasingly precise observations, their teams followed individual stars as they raced through tight orbits around something they could not see directly. One star in particular, known as S2, completes an orbit in roughly 16 years. At its closest approach, it sweeps around the central object at thousands of kilometers per second. From these orbital motions, astronomers can calculate the amount of mass required to produce the observed gravitational field. The answer is roughly 4 million times the mass of the Sun, and that enormous mass is concentrated inside an astonishingly small region. There are very few known physical objects capable of satisfying those constraints. A supermassive black hole fits them naturally. The orbital measurements also allow astronomers to test relativistic effects in strong gravity. As stars pass close to Sagittarius A star, their motions and the light they emit reveal subtle deviations from simple Newtonian expectations. These are exactly the kinds of effects predicted when spacetime is strongly curved. But stars are only one line of evidence. Matter falling toward black holes produces another. Gas approaching a black hole can settle into a rapidly rotating accretion flow. Friction, turbulence, magnetic fields, and orbital motion can heat this material to enormous temperatures. The black hole itself remains dark, but the matter surrounding it can shine brilliantly. In stellar mass black hole systems, this hot material can produce intense X-rays. Around supermassive black holes, accretion can power some of the brightest objects visible across cosmic distances. The radiation coming from these regions carries information about motion deep within a strong gravitational field. Spectral features can become broadened and distorted by extreme orbital velocities, gravitational redshift, and relativistic effects. Rapid changes in brightness also provide useful clues. If an astronomical source changes noticeably over a short period, the emitting region cannot generally be enormously larger than the distance light could travel during that timescale. Very rapid variability therefore points toward compact emitting environments. Then there are relativistic jets. Some accreting black holes are associated with narrow streams of plasma launched outward at speeds close to the speed of light. These jets can stretch for thousands or even millions of light years. Importantly, the material in the jets is not being fired from inside the event horizon. The launching process occurs in the surrounding accretion flow and magnetic fields outside the horizon, where matter and energy can still escape. The existence of jets does not weaken the idea of a black hole. Instead, they reveal just how energetic the environment outside one can become. Another completely different form of evidence arrived on September 14th, 2015. The Laser Interferometer Gravitational Wave Observatory detected a brief distortion passing through Earth. The signal lasted only a fraction of a second, but its shape was extraordinary. It matched the predicted gravitational waves produced when two black holes spiral together and merge. The objects had masses of roughly 36 and 29 times the mass of the Sun before the merger. As they orbited one another faster and faster, they radiated energy through gravitational waves. Their separation shrank. Their orbital frequency increased. Then they merged into a single larger black hole. The final object settled down through a stage known as ring-down, radiating away disturbances in its spacetime geometry. This signal was remarkable because physicists were not simply detecting light from hot material around a suspected black hole. They were detecting ripples in spacetime generated by the motion of the compact objects themselves. The detailed waveform depends on the masses and spins of the objects, the way they orbit one another, the merger process, and the properties of the final remnant. General relativity predicts how those stages should behave. By comparing observed gravitational wave signals with theoretical waveforms, scientists can test whether these compact objects behave like the black holes described by Albert Einstein's theory. Many additional black hole mergers have since been observed. Together, they have transformed black holes from distant astronomical suspects into objects whose collisions can be measured through the changing geometry of spacetime. And there is yet another independent route. The Event Horizon Telescope collaboration observes black holes using radio waves. Its images of the supermassive compact object in Messier 87 and Sagittarius A star show bright emissions surrounding central dark regions. Again, the darkness is important. It is not the photograph of a solid black surface. The surrounding plasma emits radio waves. Some of those photons reach Earth. Others are severely bent by the black hole's gravity. Some pass close to the photon region and curve dramatically before escaping. Others follow trajectories that cross the event horizon and are lost from the observable exterior. The resulting ring-shaped emission and central shadow can be compared with calculations based on strongly curved spacetime. Different methods are therefore telling us related parts of the same story. Stars orbit invisible compact masses. Hot gas and plasma behave as though they are moving through intense gravitational fields. Rapid variability points toward very small regions containing enormous amounts of energy. Gravitational waves reveal compact objects merging exactly where strong field relativity predicts they should. Radio observations show the effects of extreme gravitational lensing and photon capture. None of these observations requires us to watch a photon after it has fallen inside the event horizon. In fact, if such a photon could simply return and tell us what happened, the defining feature of the horizon would have failed. Black hole science works by studying what remains accessible. We observe light bending outside the horizon. We measure matter orbiting outside it. We detect radiation produced by surrounding plasma. We record gravitational waves generated as black holes move and merge. From all of these independent clues, the same picture keeps emerging. Black holes behave like regions where space-time becomes curved strongly enough to control the paths of both matter and light. And although the horizon itself hides whatever lies beyond it, the universe around that horizon leaves us more than enough evidence to know that something extraordinary is there. To say that a black hole traps light is not really to say that it grabs hold of a photon and refuses to let go. There is no invisible hand, there is no physical wall, and there is no moment when a photon suddenly discovers that it has become too heavy, too slow, or too weak to continue. The word trapped means something much more precise. An event horizon separates events that can still send signals to the distant outside universe from events that cannot. Outside that boundary, communication remains possible. Inside it, every future directed path allowed by relativity remains within the black hole. That is the defining feature. A photon itself remains exactly what it was before. It still has zero rest mass. It still carries energy. It still carries momentum. And whenever a nearby freely falling observer measures it, it still moves locally at the speed of light in vacuum. None of those properties provides an escape route once the photon is inside the event horizon. The reason is simple in principle, even if the geometry behind it is not. The photon is already travelling along the fastest causal path nature permits. If that path does not lead back outside, there is no faster option available. This is why it helps to keep the different regions around a black hole clearly separated. The event horizon is the causal boundary. The photon sphere, in the idealized non-rotating case, lies outside that horizon and marks a region where light can follow unstable circular paths. Those photon orbits are not permanent safe havens. A tiny disturbance can send the light outward or inward. But the crucial point is that light near the photon sphere can still escape under the right conditions. The black hole shadow is something different again. It is the dark region seen by a distant observer because certain photon trajectories are captured rather than reaching the telescope. The shadow is not a photograph of the event horizon itself. It is an optical consequence of gravitational lensing and photon capture in the surrounding spacetime. Then there is the singularity predicted by the classical Schwarzschild solution. That lies deeper inside. It is not the event horizon. The event horizon can have finite curvature and can be crossed smoothly by a freely falling observer. The classical singularity is where general relativity predicts much more extreme behavior and where the theory is expected to require a deeper quantum description. A rotating black hole adds another feature, the ergosphere. The ergosphere lies outside the event horizon and is shaped by frame dragging. Inside it, remaining stationary relative to distant stars becomes impossible, but escape can still be possible from parts of the ergosphere. So even there, being forced to rotate with the spacetime is not the same thing as being causally trapped behind the horizon. And then there is the accretion flow. This is ordinary matter outside the black hole, often heated to enormous temperatures as it orbits and falls inward. It can shine brightly. It can generate magnetic fields. It can help produce jets. None of that material has to be inside the horizon. Keeping these ideas separate prevents one black hole feature from quietly taking on the properties of another. The most important boundary remains the event horizon itself. Imagine a source of light hovering just outside it. If the source emits a photon outward along a suitable direction, that photon can still escape. For a distant observer, its light may be enormously redshifted, its frequency may be reduced, its energy may be received at a much lower value. The signal may become faint and delayed. But if the emission event lies outside the horizon and the trajectory is appropriate, there remains a path to the distant universe. Move the source slightly inside the horizon and the situation changes fundamentally. The photon can still be emitted locally outward. It still travels locally at the speed of light. But its complete future-directed null path never reaches infinity. The difference between those two photons is not that one has more energy, more mass, or more determination. They begin on opposite sides of a causal boundary. This also helps separate several levels of gravitational influence that can otherwise blur together. Far from a black hole, light may simply be deflected. That is ordinary gravitational bending. Move closer, and a photon can pass through a region where its trajectory curves dramatically. With precisely arranged conditions, it may follow an unstable orbit around the black hole. move deeper still, and some trajectories are captured. Cross the event horizon, and escape ceases to be one of the possible futures. These are not unrelated mysteries. They are progressively stronger consequences of the same basic idea. Spacetime geometry determines the paths available to light. The phrase "nothing can escape a black hole" also needs one final qualification. It refers to causal escape from inside the event horizon within classical general relativity. It does not mean that absolutely nothing associated with a black hole can ever move outward. Matter outside the horizon can escape. Hot plasma can be accelerated away from the surrounding accretion flow. Relativistic jets can extend across enormous distances, although they are launched from regions outside the horizon rather than from its interior. When two black holes orbit and merge, the changing spacetime can carry gravitational waves outward. And quantum field theory predicts Hawking radiation, which allows an isolated black hole to lose energy over immense timescales. None of these effects represents an ordinary photon beginning inside a classical event horizon and simply travelling back through it. The distinction matters because the event horizon is not defined by darkness alone. It is defined by causality. Once an event lies inside, no future directed signal from that event can reach the distant exterior without violating the causal structure of general relativity. That is what being trapped actually means. A black hole does not need the photon to have rest mass. It does not need to slow light below the speed of light. It does not need an invisible surface to catch anything. The geometry itself does the work. Outside the horizon, some future paths lead away. At the horizon, the boundary is reached. Inside it, every future directed path remains deeper within the black hole. So the answer to the original mystery is not that black holes somehow discover a way to pull on massless light. It is stranger than that. Light has no rest mass, but it still has to move through spacetime. And a black hole traps light by changing the structure of spacetime so completely that once the horizon has been crossed, the outside universe is no longer among the possible destinations of the future. So how can a black hole trap light if light has no mass? The answer is that a black hole does not trap light by pulling on its rest mass. A photon has no rest mass at all. But gravity, in Albert Einstein's general theory of relativity, is not simply a force that acts only on massive objects. That older intuition comes largely from Isaac Newton's description of gravity, where masses attract one another through a force. General relativity changes the picture. Energy and momentum influence the geometry of spacetime, and matter and light then move through that geometry along the paths available to them. For light, those paths are called null geodesics. A photon still carries energy. It still carries momentum. It can transfer momentum through radiation pressure. And throughout all of this, its rest mass remains exactly zero. Nothing about gravity requires the photon to secretly become massive. Near a black hole, the important change happens to spacetime itself. Carl Schwarzschild's solution to Albert Einstein's equations revealed the event horizon of an idealized non-rotating black hole. That horizon is not a surface. It is not a shell. And it is not a wall that a photon crashes into. It is a causal boundary. A photon crossing it does not slow down. It does not stop. It does not feel an impact. Locally, it continues moving at the speed of light in vacuum. The crucial difference appears in the light cones that describe possible future directions. Outside the horizon, some future directed paths lead away from the black hole. Inside it, every future directed light path remains within the black hole. An outward signal can still be emitted locally. It can still travel at the speed of light. but it cannot connect that interior event with the distant outside universe. That is what trapped really means. The photon sphere is different. It lies outside the event horizon in the simple Schwarzschild geometry and permits unstable photon orbits. A photon there can still escape under the right conditions. The black hole shadow is different again. It is the dark region seen by a distant observer because some photon trajectories are captured while others are strongly bent around the black hole. The Event Horizon Telescope collaboration has observed this effect around the supermassive object in Messier 87 and around Sagittarius A star at the centre of the Milky Way. Real black holes also rotate. Roy Patrick Kerr's solution showed that rotation twists the surrounding spacetime through frame dragging and changes the paths available to both matter and light. The geometry becomes more complicated, but the basic rule remains. Once a future-directed causal path begins inside the event horizon, it does not lead back outside. For distant observers, the picture can look stranger still. Light emitted from near the horizon becomes increasingly redshifted. Signals arrive more slowly. An infalling object appears to fade and slow. But this does not mean that light itself is locally slowing down. Nearby observers still measure it travelling at the same invariant speed. Even Hawking radiation does not provide an escape route for a photon already inside. Stephen William Hawking's result comes from quantum fields in curved spacetime. It does not describe ordinary photons climbing outward through a classical event horizon, and the black hole picture is not merely theoretical. The orbits of stars around Sagittarius A star reveal roughly 4 million solar masses concentrated into an extraordinarily compact region. Gravitational waves from merging black holes match the behaviour predicted by general relativity. The Event Horizon Telescope collaboration has imaged the effects of extreme photon bending and capture. Different observations keep pointing toward the same description. The mystery disappears once gravity is no longer imagined as a hand reaching out and pulling on the mass of a photon. Light does not need rest mass to be trapped. It only needs to move through spacetime. And inside a black hole's event horizon, spacetime has been shaped so profoundly that moving toward the black hole is no longer merely one possible direction among many. It is part of every possible future.